Yeah, my name is Mark. I'm here to present about Chrome for iOS 101. Bit of history for iOS Chrome. We launched at the same time as Chrome for Android did in 2012. Chrome for Android, we had a long history of having a forked repository that we then had to reunify. We also don't recommend this as an approach for doing anything. Right now, Chrome is a widely used iOS app. It is usually in the top 5 or higher utility apps in regional app stores. Right now, it's the #2 utility app in the US App Store. And finally, after many, many years with iOS version 14, Chrome can be set as your default browser on devices instead of Safari. So that's a great step forward for us. Couple of facts about usage and uptake rates in iOS Chrome. Most users update iOS Chrome quite quickly. We have about 85% of users on the latest version of Chrome within about 3 weeks of a new release. This is partly due to how aggressively iOS pushes app updates. We support usually 1 or 2 iOS versions before the current one. So currently iOS 14 is the current version, so we support iOS 13 and iOS 12. Again, because of how aggressively the platform pushes updates, particularly OS updates, we usually pass what we think is a critical threshold for deprecating an older version fairly quickly. And so at that point, we will drop the N-2 version. So, when we pass that threshold for iOS 12, we'll drop support for it. That will probably happen sometime early in 2021. Aside from the benefits of being on a small number of relatively recent OS versions, one advantage this also gives us is that the minimum supported iOS device is relatively modern. I believe we no longer support any 32-bit devices, for example, and that is also helpful for our development. We have lots of iPad users. iPad users really like Chrome. And this means that we get a bit of extra effort to support iPad features and use cases. For example, we provide the kind of tabbed tab switcher, kind of like a desktop, when you have a wide enough view on your iPad. We support iPad's side-by-side multitasking, and coming very soon, we'll support a full iPad multi-window. So you'll be able to have 2 Chromium windows side by side. You can see an example there in that screenshot. So what is special and unique about iOS? Well, iOS is still Chrome, so you get all the great Chrome features. iOS Chrome is still Chrome. You get all the great Chrome features that you know and love. We support syncing of all the great things: history, bookmarks, autofill stuff. We show the doodle. We support translate, voice search, incognito browsing. All these features that people love are available on iOS Chrome. One big difference, though, is that we don't use Blink for web rendering. We use WebKit. And that means that we don't use V8 for JavaScript processing. We use Nitro. And we don't use the Chromium Net Stack for loading web pages. We use CF Network. Why do we do this? Well, we have to. Apple's App Store rules require that we use the appropriate WebKit framework and WebKit JavaScript. This wouldn't be so bad. WebKit is a perfectly good web browser engine. We actually don't get to use all of WebKit for iOS, because for iOS, the appropriate WebKit browser is a restricted version of WebKit, which is called WK WebView, which is the basic view part of it with a set of classes that we use. There's lots of things we don't get with WK WebView. WebKit doesn't have site isolation the way that Blink does. WK WebView doesn't provide any direct APIs for accessing the DOM or inspecting or interacting with the DOM. Its other APIs are very limited. They've grown some in the last few years, but they're still fairly minimal. As I said before, all the network loads go through the CF network stack, which means we can't use the Chrome network stack to implement things like Quick or the Chrome Data Saver. Features like that aren't possible for us to use. WK WebView does render out of process, so it does not share process with Chrome. And there's actually a pool of renderers that are managed by the OS, so that's kind of nice. We don't have to worry about that part of the resource management because the operating system takes care of it. So how do we build features if we don't have access to, say, the DOM directly, or the things that we would think of as the content layer in Chromium? And for us, the answer is injecting JavaScript. I'll talk a bit more about the practicalities of this later, but for almost any kind of feature that interacts with the contents of a web page, we have to write JavaScript that we inject to handle it. This is how we do autofill, how we do find in page, even the context menu when you long press on a link. We have to use injected JavaScript to detect and manage that interaction. And finally, if we're in the App Store, what about a beta channel? For every other platform, users can just decide they want to get the beta channel. You can't do that for iOS because we can't release a beta version of an app through the App Store. The App Store rules don't allow betas. Instead, Apple provides a program they call Test Flight, which is kind of like a beta channel, where users can opt into it, and then we can release a beta version of Chrome through Test Flight. It is limited in user population. Only about 10,000 users in our beta. These could be anybody, not non-Googlers. Anybody can join when it's not full, and currently it's full. And the apps that the version of the app that we submit through Test Flight still has to go through App Store review, so we can't do anything where we might try out something that wouldn't work in the App Store through beta. So we still ship the version of Chrome that we want our end users to get this way. Critically, this means that for iOS Chromium, relative to other platforms, we get a lot less feedback, both from users and in terms of, say, crashes or stability or metrics than other platforms get from beta usage. So that's something we have to be aware of when we're planning our features. I'm going to talk a bit about some of the peculiarities that you will encounter as a developer in iOS Chrome. The first thing you might find confusing is the language. iOS Chrome is, for the most part, written in Objective-C++. So that is C++ intermingled with Objective-C, which is one of the languages that can be used for building iOS apps. These are both C derivatives. They share the same compiler. They both compile with Clang. And Objective-C++ allows you to fairly freely mix C++ and Objective-C code. You can have C++ classes that have Objective-C members. You can have Objective-C classes that have C++ IVARs. You can make calls from one language in the other. So it actually allows a fairly rich hybrid of the two. This language was designed for exactly this purpose of bridging C++ stuff into Objective-C, which is really great for us because we can directly use and compile cross-platform C++ Chromium code very easily. So when we say freely mixed, we can think of sort of a spectrum of pure Objective-C on one end, yellow on the right here in this diagram, and pure C++, which is blue on the left here, and there's a range of points in between. And we sort of think of the middle as being the point where you switch from having a C++ class with Objective-C members to an Objective-C class with C++ members. So where do the parts of iOS Chrome fall on this spectrum? There's a wide variety, and basically the closer we are to being just using straight up Chromium code, the closer we are to using pure C++. We will have some implementations of cross-platform interfaces, for example, that are mostly C++, but have some Objective-C hooks in them. And then all the way further over to the right, once we get into iOS's UI, it is going to be a lot more pure Objective-C, maybe with just a few C++ calls or utilities used in them. What about Swift? You might be wondering. Objective-C was one of the languages that can be used to write iOS apps. Swift is the other. It was introduced by Apple 5 or so years ago. Swift has very good interoperability with straight Objective-C. It does not have a very clear interoperability story with C++. Certainly not anything like the degree of intermingling that we have between Objective-C and C++ is possible with Swift. So because of our heavily reliant on this sort of interop between the languages, our path to broad Swift adoption isn't clear, but we are definitely working on it. So see what we say next year in this talk about how we're using Swift, and you can find out more then. Beyond the language, for all the tooling, you'll need a macOS machine to do development. You will need Xcode, which is Apple's IDE, which the Xcode also includes all of the SDK that you will need to link against when you build. You don't actually have to do your editing and builds from Xcode. You can if you want. Some people do. Some people prefer to use other editors. The build chain is the usual sort of Chromium tools: GN, Ninja, Clang, Goma. We're doing the builds. If you build from Xcode, it will just trigger this tool chain. You can also just do it from the command line if you prefer to. This is all in the Chromium repo, so you will use depot tools for interacting with Git, Gerrit for code review. No surprises there. For testing, we also, like Android, use gtest for unit tests. We don't use Apple's native XCTest framework for writing unit tests. For integration and automated UI tests, we use a Google-authored tool called Earl Grey. It's open source. That is built on top of Apple's XCTest frameworks. So Earl Grey tests are used for writing tests for more complicated UI interactions and so on. You can build and run Chrome in a simulator that is provided when you get Xcode. You can actually do quite a lot of development in simulator. Simulators are pretty good. You can simulate all sorts of devices and things like that. You can also, if you have a iOS device, of course, you can tether it and build directly to it from Xcode as well. And for most features, we do recommend getting some sort of device testing happening. So technical constraints on building on iOS, there actually aren't that many. Probably the biggest one that people from other platforms will need to get their head around is that iOS apps can't spawn new processes. Everything is single process in iOS. I mentioned that the web rendering is out of process. That's true, but we don't have a whole lot of control over that. So iOS Chrome has to be entirely in the same process, and so we can't use any cross-platform code that presumes that multiple processes are available. Beyond that, iOS devices do tend to be very powerful, high-end, fairly capable CPUs and GPUs. The OS does aggressively manage memory, so iOS Chromium should expect to be terminated in the background fairly frequently, and it needs to be able to, when it launches, to behave almost the way it does if it hadn't been terminated in the background, so that we provide the users with a great experience there. I mentioned earlier that we adopt new OS versions quickly. This means it's cleaner for us to adopt new features. We don't have to continue to support multiple versions of Chrome which do or don't have particular features effectively. We are able to adopt new features and then effectively have them available to one fairly quickly. Memory usage can, of course, impact the availability of web renderers, but that is entirely handled by the US for the most part. The OS, I'm sorry, for the most part. The OS will provision or reap the available WebKit rendering processes as needed. The only interaction we have is that if for some reason a process, a web view that we were displaying was terminated for some reason, we'll get a notification about that and we can reload it if we need to. So in terms of the layout of the code in the Chromium repo, basically everything for iOS Chrome lives in the iOS root directory. We don't use anything in content or / Chrome. We don't use anything in content because that is Blink. That depends on using Blink. And Chrome, links in / Chrome can have dependencies directly on content. So we can't really use either of those things. So all of the basic sort of bits and pieces of the browser that are put together in Chrome, we have to build our own versions of in iOS. We can freely make use of base and net. We can use the Chrome network stack for anything that's not loading web pages. And we can use components, provided they have been constructed using the layered components pattern, which is a pattern by which there are not mandatory dependencies on content, but those dependencies are factored out, and there's a separate set of interfaces for iOS provided. The UI for Chrome is built using iKit, which is a native UI iOS framework. We don't use Chrome views. We do support web UI, but we only use it for debugging interfaces or for some non-critical user interfaces, things like a EULA page or things like that, not things with complicated UIs that the users are going to be interacting with frequently. The NTP, the new tab page, is native for us. It's not web UI. So specifically, parts of the code you probably want to be familiar with. iOS Chrome is basically the equivalent of / Chrome. Inside that, there's a browser directory, which is where most of the feature implementations are. Inside that, there's the UI directory where all the UI stuff lives. Separate from that, we have our web layer in iOS Web. This is a C++ API we've built around the WK-WebView class. That provides a interface that resembles that of the interfaces in the content layer and for other platforms. This provides a more familiar API for people who are developing cross-platform features to interact with our web layer. Then there are some utilities that iOS and Mac share that are in base, that are iOS and/or Mac specific. So if you're working in iOS Chrome, some key classes you are probably going to encounter that you'll need to know about. Web state. This represents the web contents of a single tab. It is basically equivalent to the content layer web contents class. But again, it wraps WK-WebView and our own navigation and other objects. Web state list. This represents the open tabs in a single window for one browser state. If you have 5 tabs open, you have a web state list and contains 5 web states. Both web state list and web state have a rich observer interface. And a great deal of our UI is built by just observing these classes and reacting to changes on them. Chrome browser state is the iOS equivalent to browser context, kind of like profile. It's functionally a singleton across the whole app. We're a single profile at the moment. Of course, if the user opens any incognito tabs, there will be an off-the-record Chrome browser state to parallel the regular Chrome browser state. And all of the incognito tabs will have their separate web state list for each window. Tying all these objects together is an object we call browser. This is similar in role to the desktop browser class. It is much smaller and simpler. It basically just encapsulates a browser state, and a web state list, and a few other objects. So it represents the model layer state for a single window. In terms of our UI classes, the most important ones are a scene controller. This is kind of the overall system controller object for each window. If you're on a phone, of course, you'll only ever have one window, so there'll just be one scene controller. And then browser coordinator and browser view controller are the main starting points for the UI that displays open tabs and toolbars and things like that. We construct our UI hierarchically using a tree of objects that we call coordinators. This is kind of a simplified example, but sort of at the root of our UI is the tab grid, the gridded tab switcher. That owns a coordinator for like an open tab, which is a browser coordinator, and that will have separate coordinators for things like the toolbar, the pop-up menu, and so on. Coordinators can be specific to features that only appear once, or they can be reusable. An example here is the action sheet coordinator. An action sheet is like an alert in iOS. Many classes might need to have an action sheet coordinator to show an action sheet, for example. So that's a reusable kind of coordinator. The coordinators are sort of the public API for pieces of features. Inside a feature, we use what we call a coordinator mediator pattern. If you saw Ted's talk about Android, some of these words may look familiar. We follow a similar pattern, but it's a pattern and not a framework. So how this pattern shakes out for iOS is somewhat different for how it works for Android. But essentially, the coordinator is an object that creates and owns the view controller, which is the thing that actually does the UI work in iOS, and a mediator. A mediator bridges between updates to the model layer and the view controller, and also the view controller pushes updates into the mediator, which can propagate back to the model layer. And the coordinator provides access to the model layer to the mediator, and sort of provides a gateway into other features outside of a given feature. So for example, if the tools menu wants to show settings, that is another feature outside of the tools menu. And so there would be some mechanism provided by the coordinator to the mediator for the tools menu, so it can open, say, the settings pages, for example. Some glossary stuff for these patterns. We think of a feature as a distinct part of the user interface with a well-defined role. Coordinator is a minimal public API for that feature, and then the coordinator is in an object that basically sets up the feature, connects all the necessary objects, and starts it going. Mediator is where all the business logic lives. It does all the hard work. It takes changes from model layer, which is the UI independent data and functions, like say the bookmarks model would be, it's a list of bookmarks, and then the mediator will translate that into updates for the UI. One quirk of how we've constructed iOS Chrome is that we treat the web state, which is to say the contents of a web page, we treat that as model data as a not a piece of UI. It's just another piece of model data, much like a bookmark or a history entry or something like that. And we interact with it in that way so that we can avoid coupling between web features and UI features. Earlier I talked about JavaScript injection. So we have about 40 JavaScript source files that we use to do JavaScript injection. Total about 110 kilobytes. We have to inject a lot of this every time every page loads so that we can have our features work. There's a lot of complexities to this because WK-WebView doesn't provide us with direct access into all of the iframes, for example, in a web page. So we have to kind of bootstrap. We have a class called WebFrame that abstracts over all this for injecting JavaScript recursively into iframes and messaging between them in a way that is secure and properly isolated. For any given feature, the JavaScript that it needs to be injected into the web page at some point. And so these are typically done in a mediator class or in a class called a tab helper, which is a way of extending the functionality of a web state object. You might imagine that debugging features written in injected JavaScript is hard. It is, so ideally don't write any bugs. One big caveat is that JavaScript that is syntactically invalid or does broken things will not prevent the app from compiling. You actually need to test all the stuff, ideally with automated tests, to make sure it's all working correctly. In stable channel iOS Chrome, you can navigate to Chrome //inspect, inspect the JavaScript console messages right there in the app. If you want to do more detailed debugging, unfortunately, Chrome DevTools is not something we can support, but you can use Safari's DevTools via Safari Remote Debugging. You can build a Chrome process build iOS Chrome on your Mac desktop and then you can attach Safari's remote debugger to the WK web views running inside the Chrome process. That can either be in a simulator or on a device that's tethered to your desktop machine. That's kind of an overview of some of the things you need to be aware of when building apps for iOS, building features, I'm sorry, for iOS Chrome. And I'll open the floor for questions.
Do you have a question, Mark?
Sure. Which security guarantees features are different in Chrome for iOS versus other primary platforms, e.g. no site isolation, as you mentioned? It's a good question. I'm the wrong person to ask, unfortunately. In general, we try and match other platform security guarantees as best we can within the limits of the platform. Site isolation being one case where we can't do that. Iframes in WebKit are not isolated from each other, and there's no separate process isolation necessarily for individual renderers. Beyond that, I wouldn't be able to say in particular. I'm sorry, I can't give you a detailed answer there. So, we do strive to have parity for security and privacy features, though. Any other questions?
I don't see anything on my end. We do have 3 more minutes, but it's up to you.
I'll wait 1 more minute or so in case anybody else has a question, and then we'll wrap it up. Okay, looks like no more questions. Thanks, folks, and I'll leave it there and enjoy the rest of your day.